Toshiba Device and Storage Corporation. E-learning. Basics of low dropout (LDO) regulators. Chapter 1. Introduction to low dropout (LDO) regulators. Types of voltage regulator ICs. Voltage regulator ICs are broadly classified into ICs for converting a DC voltage into a required DC voltage and those for converting an AC voltage into a desired DC voltage. Voltage regulator ICs for DC-DC conversion are further classified into linear regulators and switching regulators, also known as DC-DC converters. Linear regulators exist in two basic forms: series regulators and shunt regulators. Low dropout (LDO) regulators are a type of series regulators. Linear regulators are capable of only step-down voltage conversion. Advantages and disadvantages of linear regulators and switching regulators. Both linear and switching regulators have their own advantages and disadvantages as shown below. Step-down conversion is possible with both products, but step-up conversion, step-up and step-down conversion, and inverting conversion are possible only with switching regulators. Linear regulators have fewer part count and are less complex to design than switching regulators. Depending on the usage conditions, when using an LDO regulator as a linear regulator, the input-output voltage differential tends to be smaller than that of a switching regulator. Furthermore, output voltage ripple and noise, e.g., EMI, are smaller than those of switching regulators. However, heat generation tends to be larger than that of switching regulators. The LDO regulator may be smaller depending on the usage conditions. What is an LDO regulator? An LDO regulator is a type of semiconductor voltage regulator that is used when the required output voltage differs from the input voltage. Suppose, for example, that the input voltage is 5 volts and that the required output voltage is 3 volts. In such cases, LDO regulators provide a simple and inexpensive solution for power supply regulation. A voltage regulator with a small difference in voltage between input and output is called an LDO regulator. LDO stands for low dropout. An LDO regulator is a type of linear regulator with a low input-output voltage differential. This article describes why electronic devices require LDO regulators for stable operation and provides an overview of them. Need of LDO regulators for electronic systems. Nowadays, electronic circuits are becoming increasingly complex and power efficient to improve the performance, reduce the size, and enhance the versatility of electronic equipment. Under these circumstances, electronic circuits and ICs are shifting to low voltage operation. In addition, sensors and high-precision analog circuits require low-noise circuit design. Conventionally, power supply circuits or power management IC (PMIC) have been commonly used on a board to supply the required voltage to each circuit block or IC. Then, the power supply voltage was supplied to each circuit from the power supply circuit and the regulator IC. However, the resistance of a long board trace causes a considerable voltage drop, while crosstalk between parallel board traces tends to affect the operation of noise-sensitive devices. To solve these issues, point-of-load (POL) regulator ICs are often used to locally produce the voltage required for each circuit block or IC. Place LDO regulators and other power supply ICs close to their point of use. I provide precisely regulated voltage with low noise for the subsequent IC or circuitry and thereby improve system stability. What is a linear regulator? A linear regulator is a type of voltage regulator IC that acts as a variable resistor in response to changes in input voltage or output current in order to maintain output voltage regulation. There are two types of linear regulators: series regulators and shunt regulators. A series regulator, as the name implies, is placed in series between a power supply and a load, whereas a shunt regulator is placed in parallel between a power supply and a load. Operations of linear and switching regulators. Linear regulators cut off excessive voltage to keep the output voltage constant. In contrast, switching regulators control the on and off time to make the average value of the input voltage constant, thereby regulating the output. Principle of operation of series regulators. The left figure is a simplified series regulator schematic. The value of a variable resistor is controlled according to changes in input voltage or output current to regulate the output voltage, Vout, to a load. The right figure is a schematic of a series regulator with the variable resistor replaced by a MOSFET to explain the operation in more detail. The gate source voltage, VGS, of a MOSFET is adjusted according to changes in input voltage or output current to increase or decrease the drain source voltage, VDS, thereby regulating the output voltage, Vout, to a load. A series regulator is placed between a power supply and a load. It regulates the output voltage by adjusting the value of a variable resistor according to changes in input voltage or output current. When the output current is constant and the input voltage increases, the voltage across the variable resistor is increased by increasing the value of the variable resistor, and the output voltage is kept constant. When the input voltage is constant and the output current decreases, load resistance increases, the voltage across the variable resistor is increased by increasing the value of the variable resistor, and the output voltage is kept constant. Series regulator ICs use an active device such as a MOSFET or a bipolar junction transistor instead of a variable resistor. Circuit configuration of a series regulator. Basically, a series regulator consists of the following blocks. Output transistor. The output transistor is placed in series between the input and output pins of a series regulator. In response to changes in input voltage or output current, its gate voltage or base current is controlled by a signal from an error amplifier. As a result, the output transistor acts as a variable resistor to maintain output voltage regulation. Reference voltage source. This is a reference voltage source for the error amplifier. The error amplifier controls the gate or base of the output transistor according to this reference voltage to maintain output voltage regulation. Feedback resistors. The feedback resistors divide the output voltage to generate a feedback voltage. The error amplifier compares the feedback voltage to the reference voltage to control the output voltage. Two feedback resistors are connected in series between the Vout and ground pins. The midpoint voltage between these resistors is applied to the error amplifier. Error amplifier. The error amplifier compares the feedback voltage, i.e., the midpoint voltage of the two feedback resistors, to the reference voltage. When the feedback voltage is lower than the reference voltage, the error amplifier increases the drive capability of the MOSFET to reduce its drain source voltage and thereby increase the output voltage. When the feedback voltage is higher than the reference voltage, the error amplifier decreases the drive capability of the MOSFET to increase the drain source voltage and thereby reduce the output voltage. Differences between a 3-terminal voltage regulator and an LDO regulator. Classic 3-terminal voltage regulators, also known as standard voltage regulators, use an NPN-type transistor or an N-channel MOSFET as an output transistor. For these regulators to work, an input-output voltage differential called the dropout voltage, VDO, is necessary as shown below. In the case of NPN-type voltage regulators, the minimum value of VDO must satisfy Vin minus Vout more than R in Xi and plus 2 VB. In the case of MOSFET-based voltage regulators, the minimum value of VDO must satisfy Vin minus Vout more than R in I and plus VGS. Suppose Rn equals 1 kΩ, In equals 1 mA, VB equals 0.7 volts, and VGS equals 1 volt. Then, the minimum input voltage required to generate a 5-volt output is calculated to be 7.4 volts in the case of NPN-type voltage regulators and 7 volts in the case of MOSFET-based voltage regulators. In contrast to these regulators, LDO regulators mainly use a PNP transistor or a P-channel MOSFET as an output transistor. The minimum dropout voltage of such LDO regulators is determined by the collector-emitter voltage, VCP, S at T, and the drain source voltage, VDS equals RDS, on ID. Therefore, LDO regulators can operate with the smaller dropout voltage than 3-terminal voltage regulators. There is also a new type of LDO regulator that provides an even smaller dropout voltage, which uses an N-channel MOSFET with a smaller on resistance than a P-channel MOSFET as an output transistor and has a power supply pin dedicated to the control circuit, including the MOSFET drive circuit. Chapter 2. Convenient functions of LDO. Useful functions available with LDO regulators. LDO regulators provide various functions to ensure stable system operation. This section provides an overview of overcurrent protection, thermal shutdown, inrush current reduction, slew rate control, soft start, auto discharge, and undervoltage lockout, UVLO. The subsequent sections describe each of these functions. Overcurrent protection operation of LDO regulators. When a short circuit between a load on the V outside and ground or other system failure occurs, this function limits the output current of an LDO regulator to protect itself in the system in which it is used. Toshiba's LDO regulators provide overcurrent protection called foldback. In the event of excessive current higher than the internal threshold, foldback reduces the output current, I out, as the output voltage, V out, decreases. Even when the output voltage has reached 0 volts, the output current continues flowing at the internally set level. The term foldback is derived from the shape of the I out vs V out curve that folds back as shown below during protection operation. When a faulty condition causing an overcurrent condition disappears, an LDO regulator automatically recovers from overcurrent protection, returning the output voltage to the normal level. Thermal shutdown, TSD, operation of LDO regulators. In the event of excessive power dissipation or the junction temperature exceeding a threshold due to an excessive increase in ambient temperature, the thermal shutdown function turns off an LDO regulator to protect itself in the system in which it is used. LDO regulators have a thermal shutdown temperature and a recovery temperature. The thermal shutdown temperature is the temperature at which thermal shutdown is tripped in the event of an increase in junction temperature in order to turn off an LDO regulator. Once the LDO regulator is turned off, it dissipates no power, so the junction temperature begins to fall. When the junction temperature reaches the recovery temperature, the LDO regulator turns back on automatically and supplies the regulated voltage to the subsequent IC and circuitry. The recovery temperature is the temperature at which the LDO regulator turns back on after thermal shutdown forces it off. In the datasheets of LDO regulators, a difference between the shutdown and recovery temperatures is specified as thermal shutdown hysteresis. Once thermal shutdown is tripped, its cause must be removed to set the control pin low. If the control pin is left high, the junction temperature increases again. This causes an LDO regulator to enter the following loop: a turn-off of an LDO regulator, a decrease in junction temperature, a turn-on of the LDO regulator, an increase in junction temperature. The LDO regulator should not be left at an excessive temperature for an extended period because doing so might affect the system stability or degrade the reliability of the LDO regulator. Be sure to provide a fail-safe mechanism for a system in case of thermal shutdown. Inrush current reduction function of LDO regulators. When the input voltage rises from 0 volts and reaches the minimum operating voltage, an LDO regulator turns on to supply regulated output voltage. At this time, the internal error amplifier drives the output transistor between the V-in and V-out pins with the maximum drive capability to raise the output voltage to the programmed level. Once the output voltage reaches the programmed level, the LDO regulator tries to maintain it at that level. However, the internal circuit delay, for example, might cause the output voltage to overshoot, exceeding the rated voltage of the load IC or circuit. In addition, a large inrush current flows into the LDO regulator to charge the output smoothing capacitor connected to the V-out pin. Inrush current occurs during the period from the time when the LDO regulator turns on to the time when the output voltage stabilizes. If the V-in pin is connected with the board trace with large impedance, the input voltage might sag because of a voltage drop that occurs across the board trace impedance due to inrush current. Consequently, the LDO regulator is unable to produce an output voltage at a normal level. The inrush current limiting function prevents these conditions. After the LDO regulator turns on, it raises the output current slowly while limiting inrush current, thereby suppressing the output voltage overshoot and the input voltage drop. Therefore, inrush current limiting helps improve system stability. Inrush current limiting is also called slew rate control or soft start. Auto discharge function of LDO regulators. An electronic system consists of multiple ICs and circuits. For the system to work properly, it is necessary to set a power supply sequence, i.e., the order in which to supply power to the constituent ICs and circuits. A relatively large capacitor is connected to the V-out pin of an LDO regulator in order to smooth the output voltage. After the LDO regulator is turned off, this smoothing capacitor remains charged for a while, depending on the supply current of the subsequent IC or circuit. This makes it difficult to set the required power supply sequence. When an LDO regulator turns off, the auto discharge function discharges the smoothing capacitor quickly via the internal N-channel MOSFET connected between the V-out and ground pins, thereby simplifying power supply sequencing. Undervoltage lockout, UVLO, function of LDO regulators. System operation might become unstable if the voltage supplied to a constituent IC or circuit drops. To ensure system stability, the undervoltage lockout, UVLO, function of an LDO regulator turns off its output when the input voltage drops below the internal threshold. UVLO has hysteresis. The output automatically turns back on when the input voltage rises back above the recovery threshold with the high-level control voltage being applied. Chapter 3. Glossary of terms used in the datasheets for LDO regulators. Glossary of terms used in the datasheets for LDO regulators. The following table provides the definitions of major electrical characteristics shown in the datasheets of LDO regulators. Input voltage Vn is the input voltage range in which an LDO regulator can operate properly. Bias voltage V bias and BAD are the bias voltage range in which an LDO regulator can operate properly. The bias voltage is used as a power supply for the internal control circuit. Output voltage accuracy Vout is the accuracy of the minimum and maximum output voltage regulation relative to the typical value under the test conditions specified in a datasheet. Adjustable voltage VADJ is the reference voltage for the internal error amplifier. VADJ is specified for LDO regulators whose output voltage can be adjusted arbitrarily with external resistors. Quiescent current IB and IB on are the quiescent current of the internal circuitry minus the pull-down current of the control pin flowing out of the ground pin when an LDO regulator is operating under the test conditions specified in a datasheet. Quiescent current IN on is the quiescent current flowing into the VN pin when an LDO regulator is operating under the test conditions specified in a datasheet. Quiescent current I bias on is the quiescent current flowing into the V bias pin when an LDO regulator is operating under the test conditions specified in a datasheet. Standby current IB off, IN off, and I bias on are the current flowing through the VN and V bias pins when an LDO regulator is in standby mode with VCT equals 0 volts. ADJ pin current IH is the input current to an error amplifier connected to the VADJ pin. IH is specified for LDO regulators whose output voltage can be adjusted arbitrarily with external resistors. Control voltage on VCT on is the voltage required at the control pin to turn on an LDO regulator. When a voltage in the range specified in a datasheet is applied to the control pin, output voltage appears at the Vout pin. Control voltage off, VCT off, is the voltage required at the control pin to turn off an LDO regulator. When a voltage in the range specified in a datasheet is applied to the control pin, an LDO regulator shuts down. Control pull-down current ICT is the current that flows through a pull-down device connected between the control and ground pins of an LDO regulator. Line regulation, reg line, is an amount of change of the output voltage, Vout, with respect to the input voltage, Vin. LDO regulators with a smaller reg line value have a higher ability to maintain Vout regulation despite changes to Vin. Load regulation, reg load, is an amount of change of the output voltage, Vout, with respect to the output current, Iout. LDO regulators with a smaller reg load value have a higher ability to maintain Vout regulation despite changes to Iout. Dropout voltage VDO is a difference between input and output voltages necessary to maintain output voltage regulation. Also called the input-output voltage differential. Current limit ICL is the specified current value at which an LDO regulator begins limiting excessive output current in the event of overcurrent protection being tripped. Undervoltage lockout threshold voltage UVLO is the input voltage of an LDO regulator at which its undervoltage lockout, UVLO, function is tripped. Temperature coefficient TCVO is a rate of change of the output voltage with respect to a change of 1 degrees Celsius in ambient temperature under the test conditions specified in a datasheet. LDO regulators with a smaller temperature coefficient value have a higher ability to maintain output voltage regulation despite changes in temperature. Output noise voltage VNO is the magnitude of noise that occurs at the output of an LDO regulator. Ripple rejection ratio RR, VN, and RR, V bias, are the ability of an LDO regulator to suppress ripple in the input or bias voltage. It is expressed in decibel. LDO regulators with a higher RR value have a higher ability to suppress ripple. Use RR as a guide when selecting LDO regulators for power supplies for sensor, analog, and other highly noise-sensitive circuits. The ripple rejection ratio is also called the power supply rejection ratio, PSRR, or the supply voltage rejection ratio, SVRR. Low transient response delta Vout is an amount of change in the undershoot and overshoot of the output voltage for a load current step change. LDO regulators with a large delta Vout value might affect the correct operation of a system. Output discharge on resistance RSD is the on resistance of the internal N-channel MOSFET connected between the Vout and ground pins of an LDO regulator. Thermal shutdown temperature TSD is the junction temperature at which thermal shutdown is tripped in the event of excessive power dissipation or an excessive increase in ambient temperature. Thermal shutdown temperature hysteresis TSDH is a difference between the temperature at which the LDO regulator trips thermal shutdown and the temperature at which it recovers from thermal shutdown. Chapter 4. Efficiency and Power Loss Calculation for LDO. Efficiency of LDO regulators. The efficiency of an LDO regulator can be calculated as follows. Input power, Pin, and output power, Pout, can be calculated using equation 2 and equation 3, respectively. When the quiescent current, IV, of an LDO regulator is negligibly smaller than the input current, IN, equation 2 can be approximated as follows. Substituting equations 3 and 4 into equation 1, we obtain. In the case of series regulators, IN equals Iout. Hence, eta equals Vout per volt IN. So, the efficiency of an LDO regulator can be calculated as the ratio of input voltage, Vin, to output voltage, Vout. Therefore, an LDO regulator can be used to compose a high-efficiency power supply, depending on the input and output voltage conditions. Calculating the power dissipation and junction temperature of an LDO regulator. The power dissipation, P, of an LDO regulator can be calculated as follows. When the term V and IB is negligibly small, equation 1 can be approximated as follows. The junction temperature Tj of the LDO regulator can be calculated as follows. Where RTH, J, is the thermal resistance of the LDO regulator when it is mounted on a board. If RTH, J, is not shown in the datasheet, you can calculate it from the power dissipation, PD, value. Substituting equation 4 into equation 3, we obtain. Suppose that Tj max equals 150 degrees Celsius, PD equals 600 milliwatt, Vn equals 3.6 volts, Vout equals 1.8 volts, Iout equals 100 milliwatt, Ta equals 40 degrees Celsius. Then, Tj is calculated as follows. Note that the power dissipation and thermal resistance values in the datasheet are the values under the specified board conditions. It is therefore necessary to evaluate LDO regulators carefully to ensure that they work properly under actual usage conditions. Chapter 5. Precautions for use. Usage considerations for LDO regulators. This section describes the considerations for system design using LDO regulators. Reverse biasing condition of an LDO regulator, i.e., output voltage higher than input voltage. If the output voltage of an LDO regulator becomes higher than the input voltage, current flows in the reverse direction from the output pin to the input pin. This reverse biasing condition could degrade or destroy the LDO regulator. If this could occur, connect a bypass diode between the Vin and Vout pins as shown in figure. Or add a reverse current blocking diode between a power supply and the Vin pin as shown in figure. When you use a reverse current blocking diode, exercise care as to a voltage drop due to the diode's forward voltage, VF, in order to ensure that the LDO regulator operates properly over the input voltage range. A diode with low forward voltage, VF, and leakage current, IR, should be selected, taking the derating of reverse bias voltage, VR, and forward current, IF, into consideration. Using a ceramic capacitor to smooth the output voltage. Ceramic capacitors are ideal for use with LDO regulators since small ceramic capacitors are becoming available with large capacitance and small equivalent series resistance, ESR. However, the values of ceramic capacitors depend on voltage and temperature as shown below. In particular, the value of the output capacitor greatly affects the negative feedback operation of an LDO regulator. Be sure to fully evaluate a system, taking voltage and temperature into consideration.